Water is a valuable resource. Effective treatment of wastewater is essential for the health and safety of the environment and the human race. According to UNESCO, up to 90% of wastewater in developing countries flows untreated into rivers, lakes, and highly productive coastal zones, threatening health, food security, and access to safe drinking and bathing water. With growing industrialization and urbanization worldwide, the need for effective and efficient removal of waste becomes more necessary. With an increasing population comes an increase of waste, which needs to be assimilated into the environment without causing harm to the environment and population. Of particular danger are organic loads and pathogenic microorganisms, which can come from domestic sewage, industrial effluents, agricultural waste, and urban runoffs. One method to treat an increase in these pollutants is to use waste stabilisation ponds. One of the most common wastewater treatment techniques is the use of waste stabilisation ponds. These systems have been in use worldwide for over 60 years and have shown to improve water quality by up to 95%. The main function of these ponds is to reduce pathogenic contamination, suspended solids, oxygen demand, and nutrient enrichment. By using beneficial organisms, these ponds stabilise wastewater, which allows the end product to be released into the environment without any adverse effects. It is proven to be one of the cheapest and most effective methods to remove particles from wastewater, and as a result is often the first choice of treatment in many parts of the world. Waste stabilisation ponds are particularly well suited to areas with warm or temperate climates with small to medium-sized communities, but they have also been used effectively for large populations.
There are three types of stabilisation ponds, classified by the type of biological activity that occurs in each pond. Generally, these types of ponds are designed in series in order to maximise their overall pollutant removal efficiency. The size of the system is often related to the amount of land available and the quality and quantity of water that needs to be treated. Most anaerobic ponds have a length-to-width ratio of less than 3 to help prevent sludge forming close to the wastewater inlet. Facultative and maturation ponds typically have a length-to-width ratio of up to 10 to approximate plug flow conditions. This is theoretically the most efficient hydraulic system for achieving pollutant removal, allowing water to move through the system with no mixing. Depth is also an important consideration. To prevent the growth of nuisance vegetation, a minimum depth is necessary. Typically, pond depths vary between 0.9 and 1.5 meters, with anaerobic ponds always deeper than the facultative or maturation ponds to allow for more settlement of solids. Studies have shown that pond depth could be increased beyond 1.5 meters, particularly in tropical countries where there is more light available. In these cases, deep ponds may still be able to achieve very high removals of BOD, excreted bacteria, and viruses. Generally, the deeper the pond, the lower the bacterial die-off rate, which in turn reduces the pond efficiency. Although shallow ponds produce a better effluent than deeper ones at equal detention time, the former require a larger area to treat waste of equal strength. Hence, there is the need to always strike a compromise during design between efficiency and area needed. The first type of pond performing primary treatment is anaerobic ponds. These deep ponds operate under heavy organic loading and, as the name suggests, contain no dissolved oxygen. Anaerobic ponds encourage the growth of algae with bacteria to break down organic waste products via the process of anaerobic digestion. The main mechanism of biochemical oxygen demand removal in anaerobic ponds is by sedimentation of settlable solids and subsequent anaerobic digestion in the resulting sludge layer. The anaerobic pond typically uses the anaerobic bacteria to break down the organic matter in the wastewater, which leads to a release of methane, carbon dioxide, and ammonia. Anaerobic ponds function similarly to septic tanks except without a lid. With intensive temperatures above 15 degrees Celsius, the pond surface bubbles due to the release of biogases, with the increase in biogas production occurring with an increase in temperature. The increase in temperature therefore results in an increase in BOD removal. Changdon describes anaerobic digestion as a two-stage process. The first stage is putrefaction, which is the bacterial degradation of organic matter into organic acids and new bacterial cells, which can be seen in the chemical equations where the organic matter, CH2O, is reacted with bacteria to form 2Q, an organic acid. During the second stage, methanogenesis, methanogenic bacteria break down the products of putrefaction, which will be the organic acid, into methane, carbon dioxide, water, ammonia, and new bacterial cells. The most efficient retention time period for the wastewater to stay within the anaerobic pond in order to decrease BOD values is up to 5 days.
The second pond used in wastewater stabilisation is a facultative pond, named after the facultative bacteria that populates them. Facultative ponds have 3 biologically active layers and can be between 1 to 2 metres deep. Their main function is converting effluent from the anaerobic pond into carbon dioxide, water, and new bacterial and algal cells. They also reduce the amount of disease-causing microorganisms. In the top layer, organic waste is degraded aerobically due to the presence of dissolved oxygen produced by the photosynthesis of the algal layer. This top layer is generally up to 500 ml deep, as this is the depth in which the sunlight can penetrate the water. Oxygen is also introduced through the natural stirring, which is caused by the wind. In the chemical equation, the organic matter reacts with oxygen and bacteria to produce carbon dioxide and water. In the middle layer, some dissolved oxygen may be present, fed from the upper layer. Facultative bacteria are dominant in this layer and are capable of responding to both aerobic and/or anaerobic conditions. In the bottom layer of the pond, with a similar process to the anaerobic pond, sludge accumulates and organic matter in this layer is degraded anaerobically. Organic nitrogen, organic phosphate, and organic sulfur undergo a reaction with bacteria in the bottom layer to reduce the amount of these organic matters. Through the use of anaerobic and facultative ponds, an overall removal of 95% of BOD can be achieved. Maturation ponds are last in the stabilisation pond system and are primarily designed for tertiary treatment. Maturation ponds are very shallow ponds with a maximum of 1 metre depth, often occupying very large surface areas. The primary function of the maturation pond is the reduction of pathogenic organisms. There are several processes within maturation ponds that remove pathogenic organisms, including sedimentation, solar UV radiation, high temperatures, and pH levels. The overall size and number of maturation ponds that are needed in series is found by calculating the required retention time in order to achieve a specified pathogen concentration. Maturation ponds are generally well oxygenated throughout the day due to the population of algae. The oxidation process removes pathogens and fecal coliforms effectively. Maturation ponds remove more nitrogen and phosphorus than the anaerobic and facultative ponds, but only remove a small amount of BOD. Maturation ponds are mainly used when a large amount of pollutant removal is required or when the water is required for the use of irrigation of crops. The maturation ponds are also usable as a buffer for failures within the facultative pond process.
There are a number of factors that influence the design of stabilisation ponds. The WHO provides a comprehensive list of design considerations, including waste classification, waste characteristics, hydrology and meteorology, light, topography, regulations and public health data, and use of effluent. Murrah and Parsons suggest that the four most important parameters for design are temperature, net evaporation, flow, and biochemical oxygen demand. The temperature used in the design is usually calculated through measuring the mean air temperature in the coolest month, quarter, or period of the irrigation season. Net evaporation is only considered during the design of the facultative and maturation ponds, because a scum layer generates on top of the anaerobic pond that prevents evaporation. Net evaporation is determined through the evaporation minus rainfall, and for this calculation, the net evaporation rates in the month used for selection of the design temperature shall be used. Usually, the flow design value is 80% of the in-house water consumption. The design can be based on similar socio-economic status and water use practice of local experiences in sewered communities. The loadings of biochemical oxygen demand per meter cube per day should have a normal range of loading between 100 to 400 grams. If located in a warm climate, i.e. in the range of 27 to 30 degrees Celsius, the amount of loading may be greater, but can cause increased sulfate and odour. Biochemical oxygen demand can be measured from the existing wastewater. If this is not possible, then the biochemical oxygen demand can be estimated through several formulas. Depending on whether the final effluent is to be used in agriculture or aquaculture, numbers of fecal coliform and Helminth egg numbers are also important. The advantages of waste stabilisation ponds over the conventional wastewater treatment systems are significant, especially in less developed countries where the cost of land is relatively low. Waste stabilisation ponds produce no treatment by products and offer high operational reliability under varying conditions, such as low wastewater flows and design temperatures. Conventional systems often require regular, highly skilled maintenance, which may be too expensive or difficult to find in developing countries. They also involve the use of mechanical treatment systems, which can be energy intensive. In less developed countries, reliance on energy-intensive mechanism is not desirable as energy supplies may not always be reliable. Waste stabilisation ponds do not require skilled personnel and use only minimal energy, making them a favourable alternative. One considerable advantage over the conventional wastewater treatment technologies is the very high removal of fecal coliform, Helminth eggs, and nematodes. Conventional systems can only achieve pathogen removal with tertiary treatment, such as chlorination.
Although waste stabilisation ponds have major advantages in less developed countries, conventional systems remain the norm in developed countries as they may not face the same constraints. This demonstrates that while wastewater stabilisation ponds have several advantages over conventional systems, they may not be the most economical or practical system in all circumstances.